Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. What if everything you thought you knew about the beginning of the universe was wrong? For over a century, the Big Bang Theory has held the reins as the cornerstone of modern cosmology. It's the story we've been told since childhood, the cyclic, explosive birth of the universe, born from a singularity, a point so small and infinitely dense that it defies our imagination. The universe, as we know it, expanded rapidly from that singularity, spreading out space, time, and matter across the cosmos. It's an elegant, almost poetic origin story, a universe coming into existence in a brilliant flash of energy. But what if that's not the whole story? What if the Big Bang Theory, this foundational narrative of the universe's birth, is incomplete, or even wrong? Astronomers and physicists are currently facing the unsettling possibility that the origins of the universe might be more complicated than we ever imagined. New evidence is emerging. Evidence that challenges the very framework of the Big Bang, evidence that could force us to rethink our cosmic history from scratch. Imagine this: astronomers armed with powerful new telescopes, advanced computational models, and a deeper understanding of quantum physics are questioning the long-standing narrative of the universe's origin. Could these new discoveries signal the end of the Big Bang Theory as we know it? To understand why these recent challenges are so significant, let's take a step back and explore just how the Big Bang Theory came to dominate the world of cosmology. It's more than just a theory, it's been the guiding framework for explaining the creation and evolution of everything in our universe. The evidence for the Big Bang was initially built on several key observations that seemed to confirm its accuracy. One of the most famous pieces of evidence was the discovery of cosmic microwave background radiation, the faint afterglow of the Big Bang itself, which had been predicted long before it was observed. This radiation, detected in the 1960s, seemed to confirm that the universe began in a hot, dense state before expanding outward. For decades, the theory grew stronger with more supporting evidence. The observed redshift of distant galaxies, for example, revealed that galaxies are moving away from us, indicating that the universe is expanding. This observation was crucial because it showed that the universe wasn't static. Instead, it was stretching out over time. The farther away galaxies are, the faster they're receding from us, a phenomenon known as Hubble's law, named after the astronomer Edwin Hubble. This expanding universe seemed to be the direct consequence of a massive explosion, the Big Bang. But as time has passed, new discoveries and new methods of observation have revealed cracks in this seemingly perfect narrative. These cracks have forced cosmologists to question whether the Big Bang Theory is the entire story of the universe's origin. And here's where things start to get interesting and controversial. A new generation of scientists, using more powerful tools than ever before, is beginning to question the very foundations of this theory. So what is this new evidence that's causing such a stir in the scientific community? One of the key challenges to the Big Bang Theory comes from the study of the cosmic microwave background, or CMB. This faint radiation, which serves as the echo of the Big Bang, has been studied in great detail by satellites like the MAP, Wilkinson Microwave Anisotropy Probe, and the Planck Observatory. These satellites have mapped the CMB with extraordinary precision, and what they've found has been surprising. For years, the CMB was considered the final, irrefutable evidence of the Big Bang. But as researchers examined the data more closely, they noticed something odd: anomalies in the radiation pattern. There were fluctuations in the CMB that didn't align with what the Big Bang model predicted. These irregularities are subtle but profound. In a universe that was supposed to be homogeneous and uniform right after the Big Bang, why would the CMB radiation show such inconsistencies? Some scientists are suggesting that these irregularities might not be random at all. In fact, they might point to the possibility of something much more complex happening at the dawn of the universe. Perhaps an event not of a single Big Bang, but something else entirely. But that's not all. Another discovery that's raising eyebrows is the phenomenon known as dark flow. For years, astronomers have noticed something strange about the motion of galaxy clusters in certain regions of the sky. These galaxy clusters appear to be moving in a specific direction, as if they're being pulled by something far beyond the reach of the observable universe. This dark flow suggests that there might be gravitational forces at play that we can't yet explain, forces from beyond the observable universe, potentially hinting at the existence of other universes or dimensions. This revelation is a game changer. If galaxy clusters are moving in ways that can't be explained by our current understanding of the Big Bang and cosmic expansion, what's causing it? Could this be the first sign of a multiverse, a vast and endless collection of parallel universes, each with its own Big Bang or origin story? This idea was once considered purely speculative, but now, with the dark flow and other anomalies in mind, some cosmologists are beginning to take the multiverse hypothesis seriously. Lastly, there's the discovery of galaxies in the early universe, galaxies that seem to contradict our expectations. According to the Big Bang model, the first galaxies should have formed several 100 million years after the Big Bang, during a period known as the Cosmic Dawn. But astronomers have recently detected massive, mature galaxies dating back only a few 100 million years after the Big Bang, far too quickly for the universe to have developed such large structures. How could such complex galaxies have formed so soon in the universe's history? This discovery adds another layer of mystery, suggesting that our understanding of cosmic evolution might be far too simplistic. So, what does all this mean for the Big Bang theory? Are these anomalies just small cracks in an otherwise solid framework, or are they the first signs that the theory itself is flawed? Could we be on the verge of discovering an entirely new paradigm, one that explains the universe's origin in a way we've never imagined? Stay with us as we delve deeper into the shocking new evidence that's challenging everything we thought we knew about the cosmos. As we continue to challenge the Big Bang theory, we must dive deeper into some of the most fascinating and perplexing discoveries that have emerged in recent years. It's not just the subtle anomalies in the cosmic, microwave background that are causing a stir. It's the entire fabric of the universe itself that's now being questioned. Let's explore the mysterious realms of dark energy, dark matter, and the possibility of parallel universes, where the very laws of physics might be rewriting themselves. One of the most profound discoveries to emerge is the concept of dark energy, a mysterious force that seems to be pushing the universe apart at an accelerating rate. It was first detected in the late 20th century, when astronomers noticed that galaxies were not just moving away from us, but speeding up as they did. This accelerating expansion was unexpected, and it led scientists to postulate the existence of dark energy, a force that counters gravity, pulling everything apart instead of drawing it together. Dark energy is now believed to make up around 70% of the universe, but we still know very little about it. In fact, its true nature is one of the greatest unsolved mysteries in cosmology. Some scientists have suggested that the accelerating expansion of the universe could be a clue that the Big Bang theory, as we know it, needs a serious overhaul. After all, if the universe was truly born from an explosion, shouldn't the expansion be slowing down over time due to gravity? Instead, we see the opposite happening, which raises questions about what else is at play in the cosmos. But here's where it gets even more fascinating. Some of the new models coming from researchers suggest that dark energy might not be a simple force, but rather an echo of something far stranger and more complex. Could dark energy be linked to the origins of the universe itself, possibly tied to events before or during the Big Bang? Could it be a remnant of a pre-Big Bang era, or even a signal from another universe entirely? Now let's talk about dark matter, another enigma that's been lurking just out of reach of our understanding. Dark matter doesn't emit, absorb, or reflect light, which means it's completely invisible to our most powerful telescopes. Yet we know it exists because of its gravitational effects on visible matter. In fact, it makes up about 25% of the universe's mass. But if it's invisible, and we can't directly detect it, how do we know it's there? Dark matter is thought to be responsible for holding galaxies together. Without it, the galaxies we observe would be flying apart due to the forces of motion. Without dark matter, the structure of the universe itself wouldn't make sense. But the more we learn about dark matter, the more questions arise. If it exists, why can't we detect it directly? And why does it behave in such a peculiar way? Some scientists believe that dark matter might not be matter at all, but could be a manifestation of something even stranger. Perhaps a form of energy that doesn't interact with light in the same way ordinary matter does. This has led to theories suggesting that dark matter could be a key player in our understanding of the early universe, potentially providing clues about what happened before the Big Bang itself. Could dark matter be a remnant of a previous universe, one that collapsed into a singularity before our universe was born? Could the universe go through cycles of death and rebirth, with each cycle leaving behind a shadow in the form of dark matter? But the plot thickens even further. One of the most mind-bending aspects of recent research is the growing idea that we might be living in a multiverse, a vast, infinite collection of universes, each with its own unique laws of physics and its own Big Bang. In a multiverse model, our universe would be just one bubble in a sea of others, each one expanding from its own singularity, each with its own history and future. What's driving this shift in thinking? A groundbreaking discovery in quantum physics might hold the key. Some physicists are now suggesting that the strange and counterintuitive nature of quantum mechanics could be pointing toward the existence of parallel universes. In particular, the many worlds interpretation of quantum mechanics suggests that every time a quantum event happens, the universe splits into multiple realities, each one representing a different possible outcome. These multiple realities might not just be confined to different moments in time, but could exist as entirely separate universes, each one with its own Big Bang. This idea has been gaining traction among some cosmologists, and the more we learn about the quantum realm, the more it seems like a distinct possibility. Could it be that the Big Bang we know was simply one of many similar events in an infinite chain of cosmic births? And if that's true, could our understanding of the universe's origins be far more complex and far more mysterious than we ever imagined? The concept of a multiverse is still speculative, but the implications are staggering. Imagine a universe where every possible version of reality exists somewhere, each one slightly different, each one unfolding along its own unique path. It's a concept so mind-bending that it sounds like science fiction. But as the evidence continues to mount, it's becoming harder to ignore. Could our universe simply be the result of an infinite cosmic experiment, unfolding alongside countless others in a vast multiversal landscape? So with these groundbreaking discoveries and theories emerging, we must ask, if the Big Bang is not the entire story, what else is out there? Are we on the brink of discovering a new model of the universe, one that encompasses not just the birth of our own cosmos, but the birth of many, all intertwined in a vast, infinite multiverse? The answers are waiting, hidden in the dark corners of space and time. So far, we've seen how new discoveries and paradoxical evidence are shaking the very foundations of the Big Bang theory. But what if I told you the Big Bang might not have been the beginning at all? What if the universe didn't start with a singularity, but instead is part of a much larger, eternal cycle? What if the birth of our universe was just the latest chapter in an ancient cosmic story, one that stretches across eons of time in ways we can barely imagine? Let's take a deep breath and journey into some of the most radical and mind-expanding theories that have emerged from the scientific community in response to these challenges. Could the Big Bang be just one event in a vast multiversal cycle? Could our universe have been born out of the ashes of a previous one, part of an endless cycle of birth, death, and rebirth? This idea brings us to the concept of the cyclic universe, a theory that has gained significant traction in recent years, thanks in part to new advances in both cosmology and quantum physics. The basic premise of this theory is simple yet profound. The universe doesn't just expand and then die in a big freeze or a big crunch. Instead, it undergoes an infinite cycle of expansion and contraction, with each cycle representing a new Big Bang. In this model, the universe has no true beginning or end, just an eternal series of Big Bangs and Big Crunches, each one triggering the next in a never-ending loop. One of the most famous proponents of this idea is the physicist Roger Penrose, who has proposed a theory known as conformal cyclic cosmology. According to Penrose, the universe we live in right now is actually the third iteration in a series of cycles stretching back to infinity. Penrose's theory is built on the observation that, as the universe expands, it cools down and eventually reaches a state of near absolute emptiness. However, he argues that, rather than simply fading into oblivion, the universe's energy might be preserved in some way, allowing it to reboot and trigger the next cycle. This theory draws on some fascinating aspects of physics, particularly the nature of entropy. Entropy, in simple terms, is the measure of disorder in a system. The second law of thermodynamics tells us that the entropy of the universe is always increasing. Things tend to get more disordered over time. In Penrose's cyclic model, the universe's entropy would increase to such an extent that it would eventually reset, creating conditions that allow a new Big Bang to occur. Rather than everything ending in a cold, lifeless universe, the extreme entropy of one cycle might give birth to the next. Each cycle in this model is a kind of cosmic rebirth, but Penrose isn't the only one thinking along these lines. Another compelling theory, known as the ekpyrotic universe model, proposes that our universe was born not from a singularity, but from the collision of two branes, multidimensional objects, in a higher dimensional space. This model suggests that our universe might be one of many in a higher dimensional multiverse, and the Big Bang was simply the result of two branes colliding and releasing vast amounts of energy. The ekpyrotic model offers a fresh alternative to the singular Big Bang and provides a possible explanation for some of the anomalies in the cosmic microwave background. The ekpyrotic universe model is especially intriguing because it attempts to solve several problems at once, such as the so-called flatness problem, the observation that the universe appears to be flat and balanced in terms of geometry and energy density, and the horizon problem, the fact that distant parts of the universe have seemingly synchronized temperatures, even though they haven't had time to exchange information. By introducing the idea of higher dimensional branes, the ekpyrotic theory suggests that our universe might be a product of an ancient collision in a higher dimensional space, rather than a singular event occurring in a one-dimensional singularity. These ideas represent a radical departure from traditional cosmology, and they have far-reaching implications. If the Big Bang wasn't the true beginning, then what does that say about the nature of time and space itself? Could it be that time itself is cyclical, stretching infinitely in both directions, with no ultimate beginning or end? And if our universe was born out of a collision in higher dimensions, what other universes might exist out there, hidden from our view in the higher dimensional space? As if that weren't enough, there's another emerging concept known as the holographic principle, which is starting to gain popularity in theoretical physics. This principle suggests that our entire universe might be a projection of information, stored on a distant two-dimensional surface, much like a hologram. In other words, the three-dimensional universe we experience could be an illusion, a mere projection of data encoded on a cosmic boundary in higher dimensional space. The holographic principle, which has its roots in black hole physics, suggests that the entire universe could be thought of as a vast, interconnected information network. Instead of being a static three-dimensional reality, our universe might be constantly emerging and re-emerging from a fundamental, lower-dimensional structure. This theory would fundamentally challenge the Big Bang model and suggest that our universe might not have a singular point of origin at all. Instead, the Big Bang could be just a local phenomenon, a brief and fleeting moment in an eternal larger structure. All these ideas, cyclic universes, brane collisions, and the holographic principle, are part of a larger revolution in cosmology and physics, one that's pushing us to rethink the very nature of space-time and existence itself. What we're witnessing is not just a challenge to the Big Bang theory, but a revolution in how we understand the cosmos. These ideas represent a bold new frontier in science, one where the boundaries between space and time are not fixed, and where the true origins of the universe are still waiting to be uncovered. The implications of these theories are nothing short of mind-blowing. If time is cyclical, then the past and future might be more closely connected than we ever imagined. If our universe is just one bubble in a vast multiversal ocean, then the idea of a single Big Bang becomes irrelevant. Our universe could be just one piece of a cosmic puzzle, part of a much grander, much more complex reality. And here's the real kicker. If these theories are true, then our understanding of the universe's origin and its future could be far stranger and more beautiful than we ever dreamed. The universe might not have had a single birth. Instead, it might be an eternal dance, a cosmic ballet that has been unfolding for as long as time itself has existed. We've explored radical new theories, challenged long-held beliefs, and uncovered the mysteries lurking in the dark corners of the universe. But where does that leave us now? If the Big Bang theory is truly being questioned, what does the future hold for cosmology and our understanding of the universe? Are we on the verge of a scientific revolution that will redefine everything we know about the cosmos? Or are we simply scratching the surface of a much deeper, more complex mystery? The truth is, we're just beginning to understand the scale of what we're facing. The discoveries we've discussed so far, dark energy, dark matter, multiverse theory, and cyclic models, are only the tip of the iceberg. As technology advances, as we develop new tools to probe deeper into space and time, and as we continue to push the boundaries of theoretical physics, the possibilities for new discoveries are endless. One of the most exciting areas of research is the study of cosmic inflation, the rapid expansion of the universe that occurred just moments after the Big Bang. While the Big Bang theory explains the universe's overall expansion, cosmic inflation provides a potential explanation for the uniformity of the universe, the structure of galaxies, and the seemingly fine-tuned conditions that allowed life to emerge. Some scientists are now exploring whether inflation itself could be part of an even larger, more complex process. Could inflation be the first step in a multiversal process, with each bubble universe undergoing its own period of inflation, setting the stage for a new Big Bang? Meanwhile, advancements in quantum mechanics and quantum gravity are pushing the limits of what we know about space and time. As scientists explore the behavior of particles at the smallest scales, they are beginning to develop new theories about the very fabric of reality. Could the quantum nature of space-time be a key to understanding how the universe began and how it might end? The intersection of quantum mechanics and general relativity remains one of the greatest challenges in physics, but it also holds the promise of unlocking secrets that could transform our understanding of the universe. One breakthrough that could reshape everything we know is the search for a theory of everything, a single unified framework that can describe all the forces of nature, from gravity to electromagnetism to the strong and weak nuclear forces. This elusive theory has long been a holy grail for physicists, and its discovery could provide the ultimate explanation for the origins of the universe itself. If we can combine quantum mechanics with general relativity into a single theory, we may finally have the tools to understand the true nature of space, time, and the cosmos. It might even offer insights into whether the universe is truly cyclical, or if it was born from something entirely different, something we can't yet comprehend. As we venture deeper into space with advanced telescopes and space probes, we are also discovering more about the universe's most distant and oldest objects. The James Webb Space Telescope, JWST, is already uncovering galaxies that formed just a few 100 million years after the Big Bang. This incredible telescope is giving us a glimpse into the universe's infancy, allowing us to test our theories and refine our understanding of how galaxies, stars, and even supermassive black holes were formed. By studying the early universe, we may uncover evidence that challenges the traditional narrative of a singular Big Bang and helps us refine our understanding of cosmic origins. But let's not forget the role of dark matter and dark energy in this cosmic puzzle. As astronomers continue to search for direct evidence of dark matter, new technologies and experiments may provide the breakthrough we need. Understanding these mysterious forces could completely rewrite our picture of the universe and perhaps even lead to a new paradigm in cosmology. Could dark matter and dark energy be clues to an entirely different type of cosmic event, one that happens over vast stretches of time rather than in a single moment of explosive creation? In the search for answers, the concept of a multiverse remains one of the most tantalizing possibilities. Could our universe be just one in an infinite number of universes, each with its own laws of physics, its own version of reality? As strange as it sounds, the evidence supporting the multiverse theory is beginning to pile up. The discovery of quantum fluctuations, the study of cosmic inflation, and the growing acceptance of string theory all suggest that the multiverse might not be a fantasy, but a real and fundamental part of our cosmic landscape. If true, this would mean that our universe is only one of many, each with its own birth and death, its own Big Bang. However, the multiverse theory also raises profound philosophical and existential questions. If there are an infinite number of universes, each with its own set of physical laws, what does that say about our place in the cosmos? Are we special, or are we just one random outcome in an infinite cosmic experiment? The very notion that there could be countless other versions of ourselves, living in parallel realities, challenges our most fundamental assumptions about existence, identity, and purpose. As we explore these new frontiers, we are reminded of how little we truly understand. Every answer brings more questions, and every discovery leads us deeper into the unknown. But this is what makes cosmology, and science in general, so thrilling. The universe is a vast and mysterious place, full of wonders that we can barely begin to comprehend. And as we continue our quest for knowledge, we are reminded that the journey itself is just as important as the destination. So, as we stand at the threshold of a new era in cosmology, one where the boundaries of space, time, and reality are being pushed to their limits, we must ask ourselves, what comes next? Are we on the brink of discovering a new chapter in the story of the universe, one that will change everything we thought we knew about existence? Or are we only beginning to scratch the surface of a mystery that will take generations to unravel? With this final thought, I'll leave you with a question to ponder. If the Big Bang Theory isn't the full story, what do you think is out there, waiting to be discovered? Could the true origins of the universe be far stranger and more wondrous than we ever imagined? If you've enjoyed this deep dive into the unknown, don't forget to like, share, and leave your thoughts in the comments below. What do you think? Are we living in a multiverse, or is there something even stranger out there? Let's keep the conversation going and continue exploring the mysteries of the cosmos together.